Alright, so suppose you have a very small company with only 7 employees, and you are the founder and CEO who is really a control freak. Okay, so you are very much obsessed with tracking every minute details about your employees. In order to do it in an automated fashion, you want a face identification device at the entry of the office so that the attendance of each employee can be tracked automatically. So you would know when a particular employee has entered the office, how long he's staying in the office, how frequent he's taking breaks, and so on. So what do you do? So suppose you have got 7 employees and you collect 1288 pictures of your employees, okay, from various different angles. So you can see George Bush appearing in multiple places here and here with different angles, different expressions, and so on. And let's say these images are tensors of dimension 50 by 37 by 3. Okay, so suppose if anybody doesn't understand what 50 by 37 by 3 is, one can think of it as matrices of size 50 by 37, but 3 such matrices. Okay, and 3 indicates the fact that the images are in RGB format. So each image is a combination of pixels. There are 50 pixels here and 37 pixels here, and each pixel is represented by a 3 scalar numbers between 0 and 1, say 0 0.7, 0 0.5, and 0.4, each representing the red, green, and blue components in that particular pixel. So ultimately we will have 5550 numbers or scalars to represent an entire image in the dataset, each of them being between 0 and 1. Now the question arises, can I represent it as a point in a very large dimensional space? So the obvious answer is yes, and the dimension is 5550. So each image in our particular data set can be thought of as a point in r to the power 5550. So now let's say an employee enters with a new expression in his face, and the device takes an image of the employee. Now the device wants to identify which employee it is. So what will it do? It will compare the new image with the existing previous images. So recall that there are 1288 images that we had collected previously. So the device will compare the new image with every other previously existing images, and it can be easily seen that it is closest to this particular image of George Bush. So the device will output that the new image or the new employee that has entered is George Bush. So although each image is actually a tensor of size 50 by 37 by 3, one can always flatten it into a very long vector of size 5550. So each entry will be any scalar number between 0 and 1, and there will be 5550 many such scalars. So let me denote the images or the vectors as x and y. So the distance between x and y will be nothing but summation I running from 0 to 5550 xi minus yi whole squared. So it will involve a lot of subtraction, squaring, and summation over 5550 components. So the natural question is, can we represent it in lower dimension? And how low can the dimension be so that it still works? Alright, so let's do a quick recap on how to project a vector onto a particular line. So let me denote the original data point in red, the vector which has been projected in blue, and the line onto which these data points have been projected as green. So the projected or the projection of x onto v, so v is the line along which the data is projected, so that is given by v transpose x times v. Here v transpose x is a scalar and v is a vector. Furthermore, we assume v to be a unit vector. So what if we want to project onto a plane which is nothing but spanned by two vectors? In that case, we project onto individual basis vectors and simply add them. So suppose I want to project x onto a subspace, say capital V, which is spanned by v1 and v2. Okay, you can see it in the diagram. In that case, what we do is that, so the projection onto v1 v2 or the subspace spanned by v1 v2 of a data point x is given by v1 transpose x times v1 plus v2 transpose x times v2. Here v1 and v2 are assumed to be unit vectors. and the others are scalars. It can be observed that this particular property of projecting onto a plane can be easily extended to any subspace which is spanned by a basis given by v1, v2 up to vn. Alright, so the general formula to project a data point x onto a subspace spanned by v1, v2 up to vk, let me call it by capital V, is given by v1 transpose x times v1 and so on up to vk transpose x times vk. So this is nothing but a linear combination of v1 up to vk, where the coefficients are v1 transpose, vi transpose x in general. Here we are also assuming that vi's are all unit vectors, that is, the norm is equal to 1. We can also have a general formula to project an entire data matrix onto a subspace. It is given by x times v transpose, where v is nothing but v1 up to vk arranged as columns, and x is nothing but x1 up to xn, each of the data points arranged as rows. So x multiplied with v, which is nothing but v1 up to vk, and then v transpose, which is v1 up to vk arranged as rows, that will be equal to nothing but the first row will be the projection of x1 onto v, onto capital V, and the nth row will be the projection of data point xn onto capital V, and hence we get a n by d matrix. This is the general formula. So now the question arises, given some data, projecting onto which vector v1 is the best. So what do I mean by the best? I mean that the reconstructed data from x1, x2 up to xn should be very, very close to the original data, and the reconstructed data is nothing but the projected data, or the data points projected onto the vector v1. Let us denote x hat as the reconstructed vector. So we are interested in this particular quantity, which can be written as x hat minus x whole transpose x hat minus x. X hat is nothing but the projection of x onto v1. So what is our ultimate objective? Our ultimate objective is to minimize the reconstruction error by choosing a suitable v1. So this is indeed an optimization problem. The reconstruction error is given by the average 1 by n times. So let me remove k and write n. So 1 by n times summation I running from 1 to capital N, x I hat minus x whole transpose xi hat minus xi, right? The same thing which we had written on the right hand side. Observe that the projection of the data point x onto the vector v1 can be written as v1 transpose x times v1, assuming that v1 is a unit vector. So replacing that in place of xi hat, we will obtain this particular very, very long formula. Now this can be rewritten as v1 transpose xi whole squared minus 2 times v1 transpose xi whole square. Observe that these are scalar quantities, plus xi transpose xi. So here xi transpose xi can be ignored because it does not have the v1 term, because we are optimizing or minimizing the reconstruction error with respect to v1. So this can be rewritten as the average of v1 transpose xi whole square. Now again, by some clever manipulation, this can be written as v1 transpose times 1 by n times summation xi transpose times v1. Now this particular step I would encourage everybody to do it yourself, which is nothing but the variance along v1. In fact, I missed the negative sign. It should be the negative variance along v1. Alright, so in the previous slide we saw that minimizing the reconstruction error is same as maximizing the variance, right? And maximizing the variance means we are maximizing with respect to v1 a particular quantity, which is nothing but v1 transpose xi whole square. Now this can be rewritten or rearranged in the following fashion, where we club xi and xi transpose together, and this term turns out to be the covariance matrix corresponding to the data, and the covariance matrix is of size d cross d. and d is the size of the data or the data point. You can say each xi is in d or rt. Now, what is the purpose of having this particular or having two different formulations? The benefit is that we will now use the variance formulation in order to solve this problem and to find out V1. The variance formulation can be interpreted in a very beautiful manner. So suppose in R2 we have data points scattered in this particular fashion. Then the variance formulation says that this blue line is the best line to project onto. What does that mean? That means if you project onto these lines, the reconstruction error will be very low. That is, the difference between the projected data points and the original data points will be very low. Also, it implies that you are having the maximum variance along this line. And the fact that these two ideas coincide, that is the crux of this particular equivalence result. So to solve this problem, we will first look at something known as Rayleigh quotient plot. So what does it say? So before looking at the result, let me first define a function f from Rd to R, which is defined in this particular fashion. Now my question arises, what are the critical points of function f? So what do I mean by critical points? It means all those points where the first derivative of f is equal to 0. So the first derivative of f with respect to v can be written as 1 by v transpose v whole square, and then using the classic numerator by denominator formula. And once we obtain the derivative, we have to set it equal to 0, and then we see that this would mean v transpose v times 2 into av equals v transpose av times 2 times v, and then it can be rewritten as in this format, where v transpose av by v transpose v is an eigenvalue corresponding to eigenvector v of the matrix A. So what the theorem essentially says is that if you take v transpose av by v transpose v, then it will lie between the maximum eigenvalue of A and the minimum eigenvalue of A. So if you want to maximize this particular quantity, this quantity will be equal to the maximum eigenvalue of A. So what it means is, if v is a unit vector, we can also rewrite it as v transpose av being in between lambda min and lambda max. So we have seen a few results. One important one being that the minimization of reconstruction error is same as maximization of the variance. Now, and then we solved the maximization of variance formulation in order to see that it will be maximized when we choose v1 to be the eigenvector corresponding to the largest eigenvalue of the covariance matrix. Now we can do the same thing for v2, which is the eigenvector corresponding to the second largest eigenvalue of the covariance matrix, and we can keep on doing this until we reach a smaller dimension where we want to project the large dimensional or high dimensional data set onto. So this concludes the method about PCA. We will look at an example to understand how to put it into practice. So here we have an example where we have 6 points, all of them in R2, and we are required to compute the mean of the sample points. So the mean will be nothing but 1 by 6 times the sum of all those data points, which will be 1, 1. And we are also required to write the centered design matrix. So that will be nothing but the first row will be x1 minus mu, the second row will be x2 minus mu, and so on. And the last row, nth row, will be, which is x6 minus mu, which on computation turns out to be this. Alright, so now we have to find the principal components of this particular sample. So what do you mean by principal components? They are nothing but the eigenvectors of the covariance matrix that is obtained from the samples. And we also have to write them as unit vectors. So the covariance matrix can be written as 1 by 6 times x dot transpose x dot. So x dot is nothing but the centered design matrix. So this will turn out to be equal to 2 by 3, 1 by 3, 1 by 3, and then 2 by 3. So now first we have to find the eigenvalues of this particular matrix. So let me proceed by writing the characteristic equation, which turns out to be 2 by 3 minus lambda whole square minus 1 by 9 equal to 0. And then from here we can say that lambda will be nothing but 2 by 3 plus minus 1 by 3. So one of the values will be 1 and the other value will be 1 by 3. And 1 is the largest eigenvalue, so this will be the first principal component. So to find the principal components, we need to find the eigenvectors corresponding to these eigenvalues. So proceeding in a similar fashion, let me denote A and B as the components of eigenvector v1, v1 corresponding to the eigenvalue 1. And then it turns out to be having the equation a minus b equal to 0 and b minus a equal to 0, which essentially means that both of them are equal, so we can take them as 1 each. But to normalize it, we need to divide by the distance, so we'll get 1 by under root 2 because we want to make it a unit vector. Similarly, this can also be performed for the second eigenvalue 1 by 3. So ultimately we get v1 as 1 by root 2 1 by root 2 and v2 as 1 by root 2 minus 1 by root 2. So now we want to see which of the principal components are preferred if only one is allowed to be used. So we will obviously choose the one which has the largest eigenvalue, which is nothing but 1 by root 2 minus 1 by root 2. The second question says, what information does the PCA algorithm use to decide that one principal component is better than the other? It compares the eigenvalues, right? In fact, it chooses that particular eigenvector corresponding to the largest eigenvalue. And v1 or the first eigenvector gives lesser reconstruction error, which we showed that is equivalent to higher variance compared to the other one. That is the idea from the optimization point of view. So now we want to compute the projection of each of the original data points, right? Now how do we do that? We just have to do v1 transpose x1 times v1, which is nothing but the projection, right? And that will be equal to 1 by root 2 1 by root 2, which is v1 transpose, times 0 0, which is x1, which is a scalar, times the vector v1, right? Now that turns out to be 0 0. Similarly, you can do the same for other data points as well, x2 x3 and so on. Please do it on your own and just verify the answers with the one that is shown in the screen.